Asterios. I'm a faculty member at Delft University, and this is Kyriakos. He's a PhD student who is about to graduate very, very soon. And we wanted to share with you a research project that has been running for some years, and we have basically our first results now published, and now we can actually talk a lot about it. What this is going to be, it's going to be a tale of three cloud services. Take your canonical example of a shopping cart that needs to be checked out, and in order to check out, you need to update the stock and get paid. The very important distinction we are going to make today is that this should not only happen in an atomic way, meaning all or nothing at all, but the consistency of the global state should remain intact. Meaning, you should not have money in for stock that remains in your warehouse. You should not have subtracted stock for money you have not received. So we are talking about different states in three different databases that should remain consistent as a global view, which is what we call consistency in databases. Okay, so we are going to see multiple ways of implementing this nowadays. First, what you would have done if you were, I don't know, working 30 years ago, you would build a monolith. A monolithic application means that you are going to implement your business logic, and you will leave all of the responsibility for consistency and atomicity to the database. This means that programmers will only deal with the application logic, right? The database will ensure acidity. Everybody will be happy, except 30 years later, if you want to migrate to the cloud, weird things are happening, which we're seeing in a minute. The problem with this is that basically you cannot migrate easy, and you may not be able to scale this application very easily, right? So people came up, like 15 years ago, people started implementing microservices. Microservices means you will take the application logic of each individual component of your software, you will implement it separately, and there was always going to be one database that's separate from anything else. And if you want the services to talk to each other, you can do so with REST calls. Nowadays with Kafka, we'll get to that in a minute. The good thing about it is that this will scale better. It will allow for code modularity, and your teams in the organization are going to be able to also scale better. And you can independently scale up and down and deploy the different submodules of the system. So it looks amazing. With the problem being that this architecture here will require orchestration. So you will have to have a maybe different subsystem that will take care of the orchestration. You will have to deal with retries and idempotency. If the downstream microservice that you're trying to call is down or not, or slow, you will have to implement that in user code. And the consistency and transactions have to also take place in application code. In this case, one can implement the Sagas pattern or implement even the two-phase commit with OpenXA. So this architecture here has several advantages, but a lot of disadvantages as well. If you move this further, and you want to scale it to extreme amounts of requests per second, you may want to partition the database. Instead of REST calls, you want to replace that with something like Kafka or a message broker or a message queue. The application logic will then have to take care of, again, all of the issues that the microservice has had in the past, right? And if you're going to do this, you will end up implementing ad hoc transactions in a system that now is partitioned. It uses message brokers, and everything you want to do in there will have to be done by the programmer. So you're kind of alone out there. You won't have any system to support you with the consistency across the services. What happens with fault tolerance? All of these things will have to be implemented by the programmers. So I don't know if you follow this Instagram account. It's a yes, but account that everything looks great. You left your monolith back, and you're trying to, move on. Instead, you end up with a huge, big mess. Whoever has tried this in their company, I think you feel what I'm saying. Why is this happening? What is this huge mess here? It is that the code that your programmers are going to implement is going to be full of things that have nothing to do with the actual business logic. So the world of databases in the 80s, it's gone. Right now, you have to implement retries and atomicity and idempotency logic. You have to make sure that changes in the code and changes in the database are consistent. You have to take care of recovery. You have to take care of partitioning. You have to take care of scaling and all of the other things that are in play here. If you look at this application, basically, this is something that just some master students have developed in the university, which is the shopping cart I showed you earlier, where we marked the green parts constituting the business logic, and everything else is what we call plumbing, right? So the useful code that somebody has written is 5 to 10%. Importantly, very importantly actually, here you have to realize that it's not a trivial thing for programmers to know about what idempotency is, what is consistency, how to ensure that a distributed application in the cloud is running in a consistent manner. Very few people in the world know these things. And those normally are developers of database systems. So you are asking nowadays your developers to start developing things that only very few people in the world should be building, right? And of course, issues come from it. So the central question, basically, that we are after is whether we can get back to the 80s in 2025, meaning that we want to hide orchestration, failures, scalability, and transaction primitives from programmers and let them just focus on business logic. Why did we want to do this and why do we believe it's possible? Simply because databases did that stuff in the 80s. But the world has changed, and we are now, I think, in this period in history that we realize that we need to get back to some guarantees for programmers. Okay, so let's set some requirements. If you want, again, to develop a monolith, what do you have here? You have your application logic, and a very happy developer doing that. And after that, the state management, failure handling, and transactions in the monolith case is taken care of by the system. If you move to microservices, there is a happy developer maybe developing some application logic, but most of the work is going to be done by developers that are going to be working on state management, failure handling, messaging, orchestration, transactions, and even scaling. If part of your application moves to something more modern, like function as a service, again, if you think about it, state management, although you can offload it to cloud database, again, because those functions are stateless, has to be done by the programmer as well. The same with failure handling, with messaging, idempotency, and all of these things that we have seen. Maybe scaling will work better for you, right? So if we were, just imagine, if we were to have an ideal runtime that I will just hand it over some Python classes or Java classes, and I would tell this runtime, please run this for me, and take all of these out of the picture for me, the question is, how would this runtime look like? Even, is it possible to build such a runtime, right? Okay, so we continue. Let's talk about streaming systems, because so far it's been 9 minutes. Maybe you thought you were in the wrong conference. We are going to talk about streaming systems now. What have we gained in the streaming systems world since, let's say, the beginning of the 2010s and up to 2020? We have basically systems that can scale. We have streaming systems that can scale. Exactly once processing is a guarantee that virtually every streaming system now offers. It has been a great enabler for streaming technology to become mainstream. You can submit arbitrary second-order functions, for example, your mappers, your joins, and your reducers. If you look at whatever programs you write in systems like Flink, for example, you will see that there is 0 lines of code that deal with failure management, because the system will take care of that. There is 0 lines of code that deal with idempotency, because the system basically guarantees exactly once. And the state that basically the system has in it is partitioned and local to the business code, which makes it extremely fast. and scalable. So that's what we have with streaming systems so far, let's say, as of 2020. The problem is, and going back to our use case, the problem is that you cannot have transactions across operator states. So exactly once is a guarantee that guarantees that a message is going to have an effect on the state exactly one times, but it does not guarantee about, for instance, that the shopping cart will be checked out only if the payment has been done and the stock has been updated. The programming model of these engines is dataflow, which means for a lot of people it's quite awkward. It differs a lot from what we use for microservices, except if you do event-driven microservices, which is going to be something that not a lot of people enjoy doing. And this is because these streaming systems nowadays are tailored to analytics and not online transaction processing, right? However, why is this possible, and what is the insight that we can gain from this streaming system? The main insight is that state, messaging, and application logic are fully managed by a single system. At least that's the observation for us. That we do not separate application logic in a stateless layer and the stateful layer, like the database does its job in the transactions, but the two have been merged in current, let's say, state-of-the-art streaming systems. This has implications. Because unless the runtime fully controls state, application logic, and messaging, exactly once is impossible. And this means that unless the runtime guarantees exactly once, the failures will leak to the application logic. The moment something leaks into the application logic, it's the programmer's responsibility to take care of it, which means we will have sad programmers. The second one is that unless the runtime also offers transactional primitives for changes across pieces of state, again, the transactional primitives will leak to the application layer, which means the programmer will have to take care of them, right? Now, the claim here is that if we start, let's say, we have gone a long way with streaming systems. If we start from a streaming data flow system nowadays, we will only have to add the transactional part in it, because the rest of the problems have already been solved because they are very well understood in how we build these systems. These are actual pictures of me and Kyriakos in a very bad AI program. And now you may accuse me of the Maslow's hammer, which says if you're holding a hammer, everything looks like a nail. But hear me out. I have a story about it. If you look at this is again what we talked about, is the event-driven, partitioned microservice deployment. If you look at this deeper, this is basically a partitioned stateful streaming data flow graph that was built by hand. Right? So it's not that I'm looking at the problem as, you know, streaming systems, you want to just apply them to yet another application use case. People build streaming data flows by hand on a per application basis. They do this already. All I want to do is to put some principles in it and see how it will work. Okay, so in the last 5 years, we have been building a system that we call Styx. It's an academic prototype that implements a data flow execution engine. It ensures transactional serializability, exactly once output, and very, very low latency processing. This data flow execution engine takes care of state storage, the transactionality of very complex orchestrated function executions, fault tolerance, and also auto-scaling, which is something that we are working on at the moment. We implemented for now what we call an operator API, which very much looks like what you would build in Apache Flink, but it includes transactional serializability. And what we are working on at the moment is the durable entities. What we are going to do now is that Kyriakos is going to show you a glimpse of this system, and then we're going to talk about some other, basically how it looks on the inside.
Hi, everyone. Again, we are going to follow the canonical example of this, or the hello world of transactional cloud applications, which is the shopping cart example that Asterios also showed. And we are going also to showcase here the low-level operator API of Styx. And for starters, let's create the first operator, which is the order or the shopping cart operator. And what we have to do in Styx is to give it a name and the number of partitions. The number of partitions is essentially the max level of parallelism. And to register a stateful function to that operator, we can just use an annotator and register, for example, the createOrder function that in here takes two arguments, a context, which is a stateful function that provides functionality to the users, such as get and put to the state for state manipulations, or calls to other functions that happen in a transactional manner. And in this createOrder example, we can see a JSON-like schema, which has the paid attribute, which means if a shopping cart has been paid or not, a list of items, a user ID that this shopping cart belongs to, and the total cost. And let's move forward to the most complex function, relatively complex, which is the checkout. And in here, we can get the value of the shopping cart, which contains all the items and the total cost, and iterate over the items, for example, and call the stock operator and the function remove stock, using the key, the item ID, to route the function to the correct partition of stock and use the quantity as parameters. And do this for all the items. And then move forward to the payment operator and remove the credit from that specific user. Change the value of paid to true and put this back to the shopping cart operator. As you can notice, there is no code for exactly once processing, for transactional semantics, or fault tolerance. Everything is handled by the system itself. And if we move forward to the payment operator and the remove credit, for example, you can see that we cannot allow, for example, the credit of a user to go below 0. And at least in Styx's case, we can raise an uncaught exception, like, for example, the not enough credit exception, and then the system by itself will initiate an automatic rollback. The user doesn't have to write anything about it, just raise an uncaught exception. Now let's move forward to how the client of Styx works. And in here we are using a typical Python framework, like Flask, for example, and create some endpoints. And this is how we can submit a data flow graph to the Styx cluster. We create an object, we give it a name, and select an operator state backend. For example, it could be a hash map or an LSM-based storage. In this example, it's just a plain hash map. Set the number of partitions to each operator, add the operators to the data flow graph, and submit it to the Styx cluster. Also, the Styx client, as you can see here, provides some futures level API where we can send an event to Kafka. And this event is just which function we want to call and with which arguments. You don't have to specify any transaction IDs, idempotency keys, or anything. And then if we just retrieve the future, we can get our results back to our service. Now let's move forward to the demo section of Styx. And let me run the cluster in Docker. Let's hope it doesn't break. OK. So here we create a Kafka cluster that acts as our ingress and egress for the entire system, a Minio cluster that is for durable storage, and our own Styx cluster. Let's wait for it to get up. OK, it started. And in this workload, we are just going to perform some transactions to already populated shopping carts. Okay. We first initialize the entire database and submit the data flow graph to Styx. And if we go here, we use Locust for a load test, and we can define a number of users and how many users we create per second. In this example, we're just going to spawn 1,000 users. And let's get this started. Let me zoom in here. So Locust submits a lot of checkout transactions. Right now, it submits 1,000 checkouts per second, and we can see a quite low latency of 32 milliseconds with a 95th percentile of 64, and it keeps dropping because it also has some startup grace period. And we have also created a Grafana dashboard to monitor the entire system. We provide the typical metrics such as CPU utilization with memory, the ingress and egress network, how many transactions per second are getting committed, and the transaction latency. We can also have some transaction-based metrics like the abort ratio, because if a lot of transactions roll back due to concurrency issues, not user-defined aborts, we would like to have this monitored. Also have the snapshot latency and the latency breakdown of the transactional epoch. And also some heartbeat metrics to see whether the cluster is still alive or not. Yeah, and that concludes the demo. Asterios will continue with some of the future work that we are going to perform on Styx.
Yeah.
Thank you.
Can you hear me? Yeah. So let me get back to what we were discussing about the system. So let me just give you a glimpse of how, let's say, what are the design decisions behind this system. First of all, something that I will show you in a minute, we decided to have an object-oriented API, just like you have microservices with calls on them. We want to have objects that store state, that is transactionally managed, and that there are functions on those objects. We want to keep the data moving, meaning we want to skip two-phase commits because those are too slow and they don't really fit the data flow model of processing because iterations bring a lot of issues. That's why we have implemented the deterministic database protocol to avoid it. We want scalability, and what we have done is for every set of objects of the same type, we simply partition them on different workers, and that's exactly how you can split them on different machines. And whenever you want to operate on a piece of state, that state will be guided through the partitioning function, and you will end up in the right machine to make the changes. We opted for coarse-grained fault tolerance, meaning asynchronous checkpoints, meaning we are doing basically a variant of the Chandy-Laporte algorithm that maybe all streaming systems implement nowadays. Via the determinism that the system guarantees, we can also guarantee exactly one's output. This means that whenever there is a result coming out of the system, even if the system replays things, the result will only show up once on your Kafka logs. And finally, consistency. So the deterministic transaction management protocol that we implement ensures serializable consistency, which is the highest consistency level that you can have on a database nowadays. And all of these things basically are more or less based on design decisions we have been taking in the last 5 years, and they have been published work from our research team. Okay, now let me show you what happens with this object-oriented API that I have hinted. Let's say that you have two what we call stateful entities. What is a stateful entity? It's a simple Python object that holds state. What is the state? It is a set of attributes that this object has, just like in every object-oriented programming model. Which means, on the left, you will see that we have a user. The user has a username and a balance. The user also has a key, so you need to have a key, a unique key for every one of your entities. And then, if you look a bit further, we have an annotation that says transactional, which is buy an item for me. What we do with this, and I don't need to get into too many details, you have here two entities, the users and the items that, for example, I want to check out in my shopping cart. There's going to be a communication between the two, let's say, entities, just like it would happen in a distributed system or in a microservice system. First, you have to check the item price, then the price should be returned to the user entity. Then you will check if you have enough balance for that price, and then if you do, you will update the stock, which will be updated again in the item entity. The stock will also return on whether everything went well. And then if everything has completed, you will simply remove from your account balance the total price that you have paid for the specific set of items. The question now becomes, these are two programs. A failure can happen at any given moment, right? The machine fails right at the yellow part when you're checking for balance. What do you do then? Now, we understand very well data flows, which means the internal state of every data flow node will be guaranteed by the system, and the system will also guarantee you exactly one's processing. All you have to do is take this imperative code, object-oriented imperative code that you have there, and convert it first to a data flow graph, and then submit that data flow graph to your data flow system to enjoy all of the advantages. And that's what we do in this case. If you look at this on how it's actually deployed on the system, you will have operators with local state. On every one of the operators, you will have a specific set of functions that operate on that state. And again, every change on the state is going to be done with serializable guarantees. Right? OK. The result is, in fact, something that's very high throughput and low latency. We have done some experiments comparing to at least academic competitor systems. It's important to say here that this, let's say, breed of systems is not something that's out there at the moment. At least we don't know of a lot of systems that take all of these guarantees and they give them to users. So we had to rely on academic prototypes to make the comparison. And basically, the way we built the system is most of the times orders of magnitude faster than the rest. OK. Now, where can I use such a thing? Again, we are trying to find how to call this type of system. There's orchestrator systems out there. There's streaming systems out there. I would rather call this a cloud application runtime with transactional guarantees, meaning you just give me your code and I will run it for you. Where can you use it? In fact, whenever you have low latency requirements and you need true transactionality, it's exactly where you would use such a system. If you don't care about transactionality, there's a ton of systems you can use. If you do care about transactionality and low latency, basically you will fall in this breed of systems. Meaning booking, reservations, ad serving and bookkeeping, fraud detection and payments, inventory management, all of these things are actually transactional applications. Even if most developers nowadays have abandoned the idea of having them being actually transactional because the technology around us does not allow for it. OK, so to make a long story short, what you should remember from this, and then we can discuss. Transactional cloud applications are extremely awkward to build. I don't know if you have felt it or not, but if you try to do it, you will realize what I'm saying. They are extremely awkward to build, to scale, and to run. State, messaging, and transactions are not three things that three separate systems should be covering, but you should be dealing with them in a holistic fashion. All of them should be covered by a tightly coupled set of system components that maybe it's not a single system, but in the end, it should act like a single system. Streaming and data flow systems have gone a very long way in the last 10 years. We can build on top of those concepts and simply add the extra things that are missing. We do not need to rediscover the wheel here. And basically, for me, this academic exercise that we have been on to in the last 5 years actually proves that it is possible to build such an ideal cloud runtime that is transactional and scalable and fault tolerant and high performant. There will be an official release of the system as open source as soon as we get to it, actually. And I would like to ask you if you have applications and use cases for such a system, just send us an email. We'll be very, very happy to even build the application for you. Thank you.
Where do you store state?
Perfect.
You need to check the balance of your clients and so on.
Yeah, at the moment we store the state in memory and we take snapshots of it in stable storage, meaning on anything that looks like S3 or a distributed file system. It is trivial to include in the transactional protocol that an external database is going to be used, but of course with the trade-offs that come with it. And it's also something that we are doing at the moment. We simply export the state as Apache Iceberg files, and we simply run a DuckDB on top to query it.
You had this Hazelcast Jet on the slide. Is it something that you compare with them, or are you using this internally somewhere?
No, it's not something we compare, no.
Is it something that you use internally?
We have worked on it some years ago, but it's not part of the...
Gotcha.
It has nothing to do with this system. Yeah.
And just not the question, but comment. If using VS Code, there's an awesome, I heard there's awesome extension from Confluent that allows you to run your local Kafka clusters without any problems.
Nice. Yeah, I've heard of it.
If you want to learn more, tomorrow is going to be a session at the Meetup Hub by yours truly. Does anyone have any questions, comments, concerns? So, once, twice, and we... Oh, yeah, absolutely.
I wonder which API you use at Kafka level. Do you rely on exactly once from Kafka?
Yeah.
Yes, we rely on exactly once from Kafka. So the message is sent from the clients, and then we consume them within Styx. We configure Kafka to be exactly once, with all the latency drawbacks that it entails. But it's quite fast, I have to say. So, but it's exactly once.
Excellent.
We're going once, twice, times. Let's stand up. Let's do one last round of applause for our speakers. Styx, Kyriakos, thank you so much for being part of the current.